right, so let's look at your sample quiz, I guess we would call it. All right, so for your first question, it asked you, well, first off, you'll notice at the top, you'll be able to use a non-graphing calculator for this. So as you're practicing these, be sure you're using like a scientific, not a graphing. So for the first one, it says use 6 rectangles to estimate the area under the parabola y equals x squared plus 3 on the interval from 2 to 5. All right, so to begin with, number 1, it says, what is my change in x? So our formula for change in x is just b minus a over n. So we're going to do b, 5, minus a, 2 over n, and that tells us that each of our rectangles is going to be 1/2 of a unit wide. You can do that with common sense too. You don't have to use the formula if you don't want to. So we're going to start at 2, and we're going to add a half to that. So that'd be 2.5 or 5 halves. And then the next one's going to go from 5 halves to 3, and then from 3 to 3.5 or 7 halves. And then 7 halves to 4, 4 to 4.5 or 9 halves, and then 9 halves to 5. So then for number 2, it says, what is the setup for R6? So remember, R6 is a Riemann sum with 6 rectangles using the right-hand endpoints to set the height. So here's my right-hand endpoints, 5 halves, 3, 7 halves, 4, 9 halves, 5. So for the Riemann sum, out in front, I'm going to have my change in x, and then it's going to be f of that first right-hand value all the way down to f of that last right-hand value. So you'll notice the 2 doesn't get used because it was only a left-hand value. If instead this had been L6, then we would have just been using the values on the left instead of the values on the right. Then for number 3, it said, what's the setup equation for M6? So remember, M6 is when I use midpoints. So to find the midpoint of the interval 2, 5 halves, like literally, I'm just going to add them and divide by 2. So if I say 2 plus 5 halves, that's like 4 halves plus 5 halves. So 9 halves divided by 2. Dividing by 2 is the same thing as multiplying by 1/2. So that's going to give us 9/4. Now let me show you a shortcut. Instead of having to do that on every single interval, as soon as I figure out what one of them is, like this midpoint is 9/4, remember that your change in x is 1/2 or 2/4. So if I take 9/4 and I add the change in x 2/4, that gives me my next midpoint of 11/4. Add that change in x again, so add 2/4 again, there's my next midpoint, 13/4, 15/4, 17/4, 19/4. Now, if you want to go through and add each of those and divide by 2, that's perfectly fine as well. You've got the calculator to do the plug and chug stuff for you. Okay, so then our setup for M6 is again going to be the change in x out in front, and then we're plugging in each of those midpoints. So 9/4, 11/4, 13/4, 15/4, 17/4, and 19/4. All right, then for number 4, it says, okay, now go ahead and find that estimated area under the curve to 2 decimal places for that M6. So the most common mistake that I see is that you forget to take this 9/4 and actually plug it into the function and get your y value. So we want to be sure that we do that. So if f of x was x squared plus 3, and we want to find f of 9/4, we're just putting 9/4 in the place of x. So that would be 9/4 squared plus 3. So 9/4 squared is going to be 81 over 16. And if I'm going to add these two, I just rewrote 3 with a common denominator of 16 to make it easy to add them. So then I could say 81 plus 48 is going to be 129 over 16. So there's our guy right there, 129 over 16. All right, then I need to plug in 11/4. And this is going to get really tedious if I don't find a shortened way of doing this, right? So if I'm plugging in 11/4, you'll notice that I could say that's going to be 11 squared over 4 squared, 16. Plus 3, and again that 3 was 48 over 16. So if I put that over my common denominator, you'll notice the only thing that's changing each time is just this number right here. So it went from 9, and then it's 11, and then it's 13, and then it's 15, and then it's 17. So that makes it a whole lot faster and easier if all I have to do is say 121 plus 48, and then put that over 16. So that's what I did right here, 121 plus 48 over 16. And then 13 squared is 169 plus 48 over 16. And then, so we could just keep right on going. All right, and then I just added my numerators together there to get the 1,534 divided by 16. Don't forget to multiply by your change in x, that 1/2. And so that gives us our approximate area under the curve accurate to 2 decimal places. All right, then for 5 through 7, this is where we did the definition of area under the curve, integration, the long way. But you'll notice that all I asked you to do here was just set it up, not to actually evaluate it, just to set it up. So they told us that we had the integration from 2 to 5 of x to the 6th plus 3. So first off, I want to know change in x. And you'll notice your change in x formula is still the same, b minus a over n. So we're going to do upper limit of integration minus lower limit of integration over n. The only difference here is I don't have a number for n. They didn't tell me to use a certain number of rectangles. I literally leave n in there. So my change in x is going to be 3 over n. All right, then for 6, they ask us to find x sub I. So our definition for x sub I is that it's just our a value, our starting value, plus the change in x that we just found for number 5, times I. So for us, our starting value, our a value was 2. We can see that lower limit right there, 2, plus the change in x that we just found, times I. So it's going to be 2 plus 3i over n. All right, then for number 7, it said, okay, go ahead and give us the setup now. So for number 7, this was our definition of a definite integral. And what we have to do is replace the x sub I and the change in x. Okay, so I'm going to come over here, and for x sub I, we just found it right there. So I'm just going to plug that in for x sub I. And then for change in x, we found that in number 5, so I'm just going to plug that in right there. Now, we could simplify that a little bit because remember 3 over n is just a constant. So I can move that constant in front of my summation and get it out of the way. And now I have f of 2 plus 3i over n. Okay, let's think about that for just a second. F of x is x to the 6 plus 3. So if they say find f of 2 plus 3i over n, that tells me to put 2 plus 3i over n in the place of x in that function. So put 2 plus 3i over n in the place of x in that function. So it would be that quantity to the 6 plus 3. So that's the only other thing that we did right here was we just replaced f of 2 plus 3i over n. We just went ahead and plugged it in to see what we got, and we replaced it with that. So that would be our final setup. That would be what would be sitting in the multiple choice because we can only set that one up. Number 8, they asked us to change from our summation notation over to a definite integral. So for number 8, it says express this as a definite integral on the interval from 2 to 6. So there's our a and b. So on the interval from 2 to 6, that's where we get our a value and our b value. And then here's our function right here. Basically, you can just drop the I and drop the I, and that will be your function. And then remember, change in x and dx are what we swap out there to get to our definite integral. All right, then for number 9. Number 9 says the integration from 0 to 6 of a function is 5, and the integration from 0 to 9 is 12. So find the integration from 6 to 9. Okay, well, here's what we're saying. If we want to know the integration, the area under the curve from 0 to 9, it would just be the area from 0 to 6 plus the area from 6 to 9. That would give us the area from 0 to 9, right? So we can say that the area from 0 to 6 plus the area from 6 to 9 equals the area from 0 to 9. And they told us the area from 0 to 6 was 5. And they told us the area from 0 to 9 was 12. So I can just subtract 5 from both sides, and that tells me that this other piece right here is going to have to be 7. And again, that's another one of those that you can use logic or common sense on. You don't have to use the formula, whichever you like better. All right, then for number 10, we were working with the definition of the fundamental theorem of calculus. It had two parts, part 1 and part 2. So number 10 deals with the first part. So it says, find the derivative of the function. All right, so if you take the derivative of an integral, they cancel each other out. They undo each other. But there's one thing you have to be sure that you change. And remember, this was the derivative in terms of x. So we have to replace these t's in our problem with x. I can promise you one of the choices sitting there is going to be 3t to the 5th plus 7t squared plus 3. Because I have to know that you have to replace that variable. So please be sure that you switch out that variable. Also, the integral sign and the dt go together, so when one goes, they both go. All right, then for number 11, we were actually using the fundamental theorem of calculus to do our definite integrals. So step number 1, we're going to do the antiderivative, and then we're just going to plug our values in, right? Okay, so you will have your formula sheet that has the derivative and integral formulas on the front, and then it has the unit circle on the back, so keep that in mind as we're looking at this. So if we're looking for the antiderivative of cosine, the antiderivative is sine. You could check your formula sheet for that. And then we need to plug in b and a. So we're going to have the sine of b minus the sine of a. So we could look on our unit circle and see that the sine at pi was 0 and the sine at pi over 2 was 1. And if you think about it, without drawing the whole unit circle, if we start at 0 and go up 1, we're at 0, 1. If we start at 0 and go back 1, we're at negative 1, 0. The x value is cosine, the y value is sine. So you can see where they're coming from. The sine at pi is 0 and the sine at pi over 2 is 1. So 0 minus 1 would give us negative 1 there. All right, then for 12 and 13, it says a particle moves along a line so that its velocity during the time its velocity is equal to t squared minus 5t plus 4 during that time interval from 1 to 5. So we want to find the displacement and the distance. Okay, so displacement is just straight up integration. I don't have to do anything different about it. It would be just as if it was question number 11. As long as I know that displacement is integration, then it's exactly like doing fundamental theorem of calculus. So I'm going to go through and I'm going to take the antiderivative. So the antiderivative of t squared is going to be 1/3 t cubed. Antiderivative of negative 5t, I'm going to add 1 to that, so that'd be negative 5t squared and divide by that same number 2. And then antiderivative of 4 is just going to be 4t to the first over 1. All right, then I'm going to go back and plug in my values of 5 and 1. So 5 cubed is 125, so that'd be 125 over 3. 5 squared is 25 times 5 is 125, so 125 over 2. And 4 times 5 is 20, so that's where this came from. I threw that in my calculator and got negative 5/6 for that. And then I'm going to plug in 1, so that would be 1/3 minus 5/2 plus 4. So there it is right there, 1/3 minus 5/2 plus 4. Threw that in my calculator, got the 11/6. So now I'm just going to subtract. And you're looking at, for your multiple choice, whether it lists it as the exact value or the decimal approximation, you could give either one. Now, distance, on the other hand, is the absolute value of that formula, because distance can't be negative, right? And so here's where that absolute value, writing it as a piecewise and writing it as the separate pieces, is going to come into play. So first off, we need to figure out where our function is positive and negative so we know how to rewrite this. So I'm going to take t squared minus 5t plus 4, and I'm going to factor it and set each of my factors equal to 0. And I'm going to come over here and make a sign graph for myself. So I have an x-intercept at 4 and an x-intercept at 1. Pick a test point like 0. So if I plug in 0, I'm going to get a positive 4. Cross a single critical number, the sign changes. Cross a single critical number, the sign changes. And so there's my sine graph. So remember that anywhere your function